Hi everyone, so thanks for having me. So I'm going to present to you what was my job market paper. So I presented quite a lot last year, but it's the first time in person, so I'm quite happy about it. So it's more of a methodological paper compared to everything else we've seen so far. And the idea is to address, to provide tools for dynamic discrete continuous choice models. So the starting point is to say that many economic problems involve joint dynamic, discrete and continuous decisions. So the most obvious example probably is the case of labor force participation, which is discrete, and consumption choice, which are joint choices. And both of the choices are actually dynamic choices, because if you choose to work or not, you accumulate experience for the future. And if you consume too much today, you have no savings for tomorrow, okay? But you have many other examples, and I think so the next presentation is going to be about retirement and consumption, which is also a discrete continuous choice models. You have example in housing. For example, when you choose to buy a house, you are choosing simultaneously whether you want to be a renter or owner, and the house size, the corresponding house size you want to buy. You have example in IO, you have example in education, etc., etc. But the thing is, the empirical analysis of this joint model is actually fairly limited for two main reasons. The first thing is the identification is relatively difficult. So take again, and I'm going to take throughout this talk the example of labor force participation and consumption. In the data, what you typically observe is that people who work are consuming more than people who do not work. So if you plot the distribution of consumption for people who work, who are unemployed, and people who are employed, the ones who are employed consume more. But the thing is, you don't know directly. It's hard to disentangle how much of this difference is due to the fact that when they work, indeed, they get more wage, and so they can consume more. And how much of it is due to the fact that they want to consume more, and so they choose to work, okay? So it's hard to identify because you don't observe the counterfactual consumption. What will have, if I work, how much will I have consumed if I had not worked, okay? And so, if you have some unobserved taste shock for consumption, so you have some unobserved variable that I will call the taste shock for consumption. The higher my taste for consumption, the more I will consume. But the thing is, I don't know how much this taste for consumption impacts my probability to work or not. So maybe if I have a high taste for consumption, I will want to work more. And in this case, the population of people who is choosing to work is, in terms of an observed characteristic, is very different from the population who choose to not work. And so that's the identification problem. And so usually in structural work, we kind of assume it away. So an assumption that is used a lot is a timing assumption, which is to say, first, I choose to work or not. Then there is a realization of my taste shock for consumption, and I choose to consume. And in this case, the discrete choice to work or not is actually independent from the realization of the taste shock because it happens afterward. But it's quite strong to say, because if you think of consumption as being complementary to labor because you get more wages, it's quite strong to assume that. And you have other assumptions which are pretty much the same of making some specific assumption on the relation between the errors of the two terms of the continuous and discrete choice. Now, even if you make some assumption about the identification, the other problem is that it's always hard to estimate this kind of model. So, and sometimes untractable. So you know this quite well here. You are talking about dynamic models, so you have to solve for the value function or to find a method that helps avoiding to solve for the value function, but you still need to compute a lot of things. And so because of that, you need to kind of limit the number of parameters you want to include, etc. So, and you have some nice estimation method for discrete choice only, for dynamic discrete choice. So I'm thinking about conditional choice probability by Otsmiller, for example, but it does not apply directly to discrete continuous choice if you are not able to estimate and identify the choices in the first stage, in fact. And so because of the identification issue, you can. So to summarize, what I want to do in this paper is to address both of these issues, identification and the estimation, all together in order to extend the conditional choice probability approach to discrete and continuous choice problems. And to do that, what I will do is I build a constructive proof of identification and so a new faster estimation method for a general class of discrete continuous choice models that I will present to you right after that. And the identification proceeds in two ways. In the first step, what you want to do is to in the first step, you want to identify the optimal choice from the data directly. So you take your data, and I mean, I show you how the identification works, but I'm using an instrument. It's actually an identification procedure that's close to the literature on treatment effect, quantile treatment effect. And so from the data, you identify directly the conditional choice probabilities and the conditional continuous choice. Separately, you're able to disentangle them. And then from the optimal choice that are identified, you plug them back into the model and you use them to identify the rest of the primitives of the model. So typically, it's the same idea of Watts-Miller. I think you had a lecture with Professor Miller on Monday or Tuesday, but the idea of Watts-Miller is that in the data, you observe the probability that people work or not, if it's only discrete choice model. And so the insight is to say, well, there is a link between if people have a high probability to work, is because their conditional value of working is higher than their conditional value of being unemployed. And so you don't need to solve the value function because there is a direct mapping between the two. And here it's the same idea is to say, okay, but it's also working with discrete continuous choices because my continuous choice will be mapped to the Euler equation condition that I have, the first order condition. And so I can also use it in a similar way to identify the rest of the model without having to solve for the value function once. Okay, so the estimation is entirely built upon the identification. It's also in two-step procedure. And as I was saying, you do not need to solve for the value function once. And because of that, you get sizable computational gains. So in a toy model I have in the paper, it's in a two-period toy model, very simple in the paper, it's already 50 times faster than a counterpart that I computed with the endogenous grid method and simulated moments. And obviously, the more complex the model, the more complex the value function is to compute. And so the larger the gains will be with my method compared to the other. Because in fact, you only have a fixed cost of computing the first stage, so of estimating the policies in the data. And then you plug them back and you simulate forward, for example, or this kind of stuff. So it's quite faster. And so really the objective of this paper is to facilitate and spread the use of discrete continuous choice model by allowing to reduce this burden of computation. It has many applications. So in the paper, I will not present this because I think I won't have time, but in the paper, I have an example of labor and consumption at the end. I have another paper on housing where you choose to your housing tenure, whether you're a homeowner or renter, and the house size simultaneously. And I think there are many other applications that you can find in education, in IO, and that you can think about, in fact. So I'm probably going to present mostly the framework and the identification, but we'll see how much time I have left at the end. So the framework. So given you state variable X, the agent will simultaneously make one discrete choice D, here binary for the presentation, and a continuous choice C of D, so conditional continuous choice. So think of D as you work or you don't work, and continuous choice is your consumption if you work and your consumption if you don't work, okay? And obviously, we only observe the consumption of the chosen alternative. So is maximizing his payoff, so VD of, which is a function of CD, of a shock eta, of the covariate X, and he has some additive term at the end, which is epsilon D. So really here it's written in static term, but you can think of VD as a conditional value function, okay? So it can be the static, but it can also englobe like dynamic model, and I'm going to show you afterwards how you put dynamic model into this setup. So you have two unobserved ID shocks, so you have additive discrete shock epsilon D, which is quite standard in the discrete shock literature. So by its additivity, it has no impact on the consumption, but it impacts the discrete choice because it's it impacts the alternative, the probability that you will pick this alternative. And you have another shock, which is the non-separable shock eta that I call the taste shock for consumption, in fact. Very importantly, it's the same in every alternative. So in the case of consumption, it works well because it's like you have a taste shock for consumption, and it's whether you work or not, it's the same taste shock for consumption. Okay, so because it's non-separable, it will impact your continuous choice, your continuous consumption choice, and it also impacts your discrete choice because it impacts the probability that you will work or not because it's impacting your payoff entirely. Okay, and so that's the issue for the identification is because of this shock, which is impacting both choices simultaneously. So as I was saying, the example G is labor force participation, CD is consumption, X can include like all the variables we usually include, right? So family background, education, work experience, assets, income, and so on and so forth. Eta are the take stock for consumption, for example, but in the idea, it's like everything that's an observed projected to one dimension, in fact. And epsilon, that's an observed that impact consumption. And epsilon has the remaining preference shock for work or not. So in terms of assumption, we don't have that much. We have a monotonicity assumption, which is to say that the C are strictly increasing with respect to eta. So it's saying that the higher your take shock for consumption, the more you want to consume. You have independence of the shock from the covariates. And because we cannot really identify the eta part, we just normalize it to 0, 1. And so if it's 0, it's the lowest possible shock, and 1 is the highest one. So it's like quantiles of shock, if you want to think of it this way. And so the thing is, this setup like this is not identified directly. And so what you need in order to identify it, you need to have some kind of instrument also. So that's why, yeah. No, I'm going right now. Yeah, I'm going to do it right now, actually, because MD is exactly related to the instrument thing. So in order to identify the problem, you need to have an instrument W, which will impact the selection, meaning the probability that you work or not, conditional on eta and on the covariates, but not impacting the continuous choice. Okay, and in order to have that in structural form, you have this by additivity, and that's the MD term. Okay, in a very general way, you see the W only enters in the MD, and so it's independent from C, but it impacts your probability to work or not if it's non-zero, if the differential is non-zero. Okay, so it's the MD term is just a way to write in the structural model the instrument assumption, in fact, the presence of an instrument. So it's excluded from the marginality of the continuous choice by construction, by the additivity, and it's relevant if it impacts the level of utility, and so it impacts the discrete choice. Okay, and here an example in this case could be, for example, if you have switching cost in and out of employment, conditional on your current D, your past labor participation choice will not impact your consumption today. And so, but if because of the switching cost, it will impact your probability to work or not, okay, today. So it impacts D, but not C. That's an example. And so you get a triangular structure and you get this kind of reduced form. And so what I'm going to show you is that this is identified. So I don't know how much time I have exactly.
30 minutes in total, and you have like 17 minutes.
Okay. Okay, so I'm going to show you the all identification. So what's the identification problem, to state it clearly? What you observe CD, D, W, and X. But in terms of observation, you only observe the consumption in the chosen alternative. You don't know what was the counterfactual consumption choice they would have made. Yeah.
So just in terms of the exclusion restriction, I'm still trying to think through what a good exclusion restriction would look like. So just in terms of past employment, so that's going to impact lifetime resources, and that's the marginal utility of consumption, that's consumption itself, it would seem. And so in that sense, it seems as though it's still going to impact both consumption as well as employment. I'm still trying to think through exactly.
But I can't. Okay, so the question is that the past employment might not be might not be excluded because it also impacts your resources and so on in the future. Well, in this case, I am controlling for the asset, for the experience, and everything every period. So conditional on the asset, the experience, it's a good instrument. That's what I mean. Yeah. Okay, so. Yeah, so as I was saying, so you have the fact that you don't observe the counterfactual CD that makes the whole identification problem. And so you have what you observe directly in the data in this reduced form function, which is the probability that you pick D. So conditional on what is observable, so W and X, and the conditional distribution of consumption. So what is unobserved by the econometrician are the two shocks. And so what you want to identify is a conditional continuous choice policy function. So the consumption with respect to eta and X, and the conditional choice probability, which is the probability that you work or not, conditional on W and X, but also on eta. And so that's the main departure from Otsmiller CCP, is that in Otsmiller, the CCP are this object, right? But because you have no eta in the mix. And here the CCP include eta, because obviously eta will matter. And so that's the complication. Okay, so for the proof identification, it's completely abstract from X and just do everything at a given X, because it's way simpler to think about it this way. So I was telling you observe only the reduced forms. And so you can derive from this, you can derive a system for both values of the instrument using the law of total expectation. So you know that eta is following a normalization, so you put uniform. It's independent from the instrument W. And so you can just write it down by law of total expectation. And by monotonicity, C strictly increasing transformation of H. And so you can write it like this. And you have this system for both values of the instrument, meaning that basically you observe everything, you know the conditional distribution of C, but you just don't know the two policy functions, C0 of H and C1 of H, okay? And that's what you want to identify. So you have a system of two equations to identify two functions, and that's how it's, and I'm showing in the paper, but I'm going to show you the intuition is that these policy functions are identified if there exists a unique solution to the system. So it's not, and the uniqueness is actually related to the effect of the instrument. So in order to have a unique solution, you need to have, so you have two ways to write this hypothesis. So either to write it in terms of reduced form. So you need to assume that like the effect of the instrument is different on the probability to work. Okay, so that's very simple. It can be zero even at some point. At some value of eta, it can be zero as long as it's not flat. Okay, it's not zero on a flat segment. And so just the translation in structural form of this hypothesis is just an hypothesis on the M functions. So, and just under this condition, I can show that there exists a unique solution and that the problem is identified. So just to make things clearer in terms of graph, I think it's easier to understand this way. What you have in the data, so you observe the joint distribution of CD and D, okay? So typically, if you take the choice of being unemployed, you will observe two curves. So this is the joint distribution in the straight line is the joint distribution conditional on being unemployed before, and the other line is conditional on being employed before. So you switch out of employment. This is the joint distribution you have in the data. What's nice is that because you know that the past labor choice is excluded from your current consumption choice, you know that the difference between these two curves is only driven by selection, by unobserved selection. So you know that it's driven by the fact that the probability to be unemployed if you were employed before is different from the probability to be unemployed if you were unemployed before. And you have the same thing for the other choice. So for the joint distribution, whether you work or not, today you have the same difference. And so this is completely observed in the data, right? Now the thing is, by the model, you know there is a link between choosing to work and choosing not to work, because just one minus the other probability, right? And so the difference between these two curves, they are related. And in fact, so this is the equation I showed you before. So by using Bayes' theorem, you just get this relationship. And so you can just plot. In fact, you know that the difference between this curve and this curve will be the same as the difference between this curve and this curve at the same eta. Okay, so that's the insight. And so if I just plot this difference, so that I call delta F, which is the difference between the two orange curves and the two green curves, I know that for the same value of eta, that I don't observe, but for the same value of eta, this curve and this curve will have the same delta F function, okay? And because of that, I can identify the mapping between consumption when you work and consumption when you don't work. So I can identify the counterfactual consumption directly. So for example, here, if I take a consumption of, if I work and I consume 20,000, how much would I have consumed if I did not work, okay? I know it has the same delta F value. And so I know I can find it this way on the graph, okay? And once I have the counterfactual mapping, I can actually find to what an observed H they correspond, and it's done. So I have identified completely the choices, okay? So, and really the role of the instrument, the assumption on the instrument, the relevance of the instrument only impacts the shape of this curve, of this delta F curves. Because this delta F curve, there is a difference in conditional distribution with two values of the instrument. And so here you see it was super simple because the two curves were piecewise monotone, strictly monotone, but they can also have some shape like this. As long as they are not flat, it will be a point identified, and we will point identify the point. And so far we have the CC, what I call the CCCs, and now the idea is to get the CCPs, so the CCPs of the model, but it's straightforward because you have strict monotonicity of the consumption with respect to eta. So for any observation of consumption, you invert it, you get the shock, the eta shock to which it was corresponding, and then it's as if you observe the T shock for consumption directly. And so you can just run estimate the conditional choice probabilities from the data directly. Yeah, so that's it for the optimal choices. And now the question is, how do you identify the rest of the model? And I'm going to show you how it works for a dynamic model because it's mostly what interests us, right? So first, how will the dynamic model enter this setup? So imagine you have very typical model. So you have a period utility, and you have some budget constraint for the assets. So you have your state variable, which includes X tilde and the income and the asset also. And so the agent, I mean, you know it quite well. So the agent will maximize the utility with respect to D and C. And so you can get back the general form that we had before, because this term, the utility plus beta expectation of the future value function, is just the conditional value function, right? So now the problem is, if I write the problem in a general way for the dynamic thing, the instrument, so WT, is not general, without a further assumption, is not excluded from the conditional value function, because if it impacts the transition, it will impact the future value function, etc. So I need to add one additional assumption, which is to say that the instrument value, conditional on X, C, and D, does not impact the future transition. So that's why the past labor choice is a very good instrument in this case, because conditional on knowing DT, so conditional on knowing whether you worked or not today, the past working decision has no effect. Well, you know directly WT plus 1, so you don't need, it has no importance. And it's excluded from also the transition to the other XT, conditional on C and on the current XT. And if you are switching cost in the model, so switching cost will be this MD term, in fact. So it could be like just a scalar, you know, if you work before, if you need to switch it, you have a cost, but it will be relevant. So, and then in this case, if you make this exclusion restriction from the transition, you get back to the standard problem we had before. And so this is identified. And so that's kind of the point of the paper, is to say, if you are able to write your model in this way, in the last line, it's identified. It will be identified. Okay, if you can find an instrument, it will be identified like this. You just so just one point that I think is quite important. So far in the model, what I have is that eta t is IID every period. Okay, so it's not. Ideally, we will not like to remove this assumption, right? If you think of take shock for consumption, you want some kind of persistence there. But the problem is, with this particular instrument, if you use a past labor choice as an instrument, you cannot really remove this this IID assumption, because for the first period, if you think about it, your past labor choice, so at the period -1, will be correlated to the eta shock at the period -1 also, which will be correlated to the eta shock at the period 0. And so the exclusion restriction from the instrument will be violated. It's not independent from the shock anymore. And so that's why if I use as an instrument the past labor choice, I cannot have a persistence in the eta. Okay. So you have two solutions to solve this. So the first one, which is actually will be in the next version of the draft, so I will probably publish at the end of September, something like that. But it will include observe individual types in the model. Okay. In the spirit of Arcidiacono Miller. So it works quite well. Or otherwise, ideally, the idea would be to just find another instrument that fulfill all the conditions, but it's quite complicated, in fact, because this exclusion from the transition is quite hard to fulfill in dynamic model. So it's harder than in static model to find a good instrument here. But if you are able to find it only for one period, something completely unexpected that impacted your probability to work, but not your consumption, you can go from it and you have everything identified, and you can have persistent shock and so on. It will work. Yeah, and so once you have identified the shocks, the choices, you get the transition, which are also identified directly from the data. And then you just use the first order condition of the model, because the first order condition of your model are relating directly your optimal choices to the primitives of the model. So, for example, your marginal period utility and also the discount factors, they are identified by the Euler equation at the optimal choice. If you follow the paper for Escanciano et al., which was published last year. Similarly, the conditional value at the optimal continuous choice, they are identified by the first order condition with respect to the asset that you integrate out. And the difference in additive terms, the additive term and the effect of the instrument is identified by the conditional choice probabilities. So I think I'm out of time, so I'm not going to go in this section. I'm just going to go over very quickly to tell you what's also in the paper. But so the estimation is completely built upon the identification, but you have several ways to do it. So you can either go parametrically, or you can build a new non-parametric method, which is built upon this, what I showed you in the identification. So you know the inversion of these two curves, which is quite complex actually to do. So, but I'm not going to go too much over that. And so, trust me, I have an example in the paper, so it goes way faster than having to solve for the value function, in fact. Okay, skip that. I also have an application of female labor supply and consumption choice simultaneously. So you can see it's in the paper. It's using French data, which are not so great actually. So, but for consumption, it's very noisy. And yes, so the results are. I'm skipping it. I have a comparison with the Inutoy model. And so, yeah, and also one last point I'd like to point out, one advantage is that I don't need to solve for the value function. I don't need to solve for the optimal problem. And so it also avoid problems like solving for kinks in the discontinuity of discrete-continuous choice that you have in, for example, with the endogenous grid method, because you need to still solve, and I don't need that. So it's avoided out. And so, yeah, to summarize, I introduced a general framework of dynamic discrete continuous choice. I proved their non-parametric identification using an instrument. And building off of that, I built a faster estimation method. And so in the next version, I'm going to introduce an observed types, and it remains to do the inference for the estimation method if I'm using the non-parametric estimation method. And so, yeah, that's it. Thank you. So, yeah.
Thank you very much. There was actually one question which came in. Is Matteo here? Are there more questions? Matthew is here? Oh, okay, perfect. Then let's get the microphone over there. Okay, there's one question here in the room, and then, or probably some more, and then we'll also come to Joe Mullen's question.
Thanks. So I think one of the assumptions was that I can observe the CDF of the continuous choice for every state. And I just wondered about the practicalities of that. For instance, I don't know, estimating the probability of very low consumption for a very wealthy person. How would you?
John and I think Bert also had questions, so I stay here in the area. They ask their questions, and we collect them here, and then I give the microphone back to Christophe.
Do you want him to answer this one first, or
no? Let's go ahead.
Yeah. So yeah, it's a very cool paper. But the if you have a parametric utility function in your identification result, can you go back to identify the you only identify the utility value function differences? Then can you actually identify the utility function parameters itself with your approach?
I think so. I guess. Okay. Oh, this way, stay fit.
Okay. Yeah. So for the first question, you are completely right. So I mean, if you want to do everything non-parametrically, you need tons of data because you need to estimate the conditional distribution very well for every state variable. So in order to prove the identification, it's not a problem. Realistically, it will be a problem. So that's why in practice, I think the most common way would be to go parametric approach to estimate this, right? But it's just to show that identification, I can treat non-parametrically. And for the other question, if I get a parametric form, I can, so for example, I have a toy model which is parametric and I show it's identified also. So there's no problem to show. It depends on the parameterization. Sometimes I think in my toy model I have a problem with the discount factor because I make it completely multiplicative. The model is so simple that it's completely multiplicative with one other parameter, and so I cannot disentangle both. But otherwise, it works in a standard way. I think so. Yeah. So Joseph Melins, maybe. Yeah.
Okay, that was great. I was really interested, Christophe. Can you, I know that maybe somebody's worked this out already. Can you remind me or tell me what happens with asymptotics here? Because you have this non-parametric estimator that you're gonna plug in to back out the parameters. What do we know and not know in this setting?
Yeah, so I didn't present the estimation at all, but I have no idea. So far, I have no idea. So that's really what I need to do because it's fair. The non-parametric estimation method that I developed, so I don't know if you check the slide because it's on the slides or in the paper, but it's fairly new because I'm estimating the function directly. So I'm not estimating pointwise, I'm estimating complete function, and that's quite, I don't know it works for the inference and so on. So I have no idea so far. But you can do it. You can still do it in a parametric way, and you are close to GMM or maximum likelihood, and then it's fairly standard, right? So it's like you have the drawback of two-step method because you estimate the first step and then the second one.
Mm-hmm.
So that's.
But then, yeah, okay, yeah. You don't have to teach me econometrics right now, but that answers my question. Thank you.
Yeah, so I was just wondering about some of the practicalities of this. You know, we've seen that the discrete choices, they tend to generate multiple solutions in the Euler equations. And I guess since you're using those as moment restrictions, you might get like, you know, multiple, lots of minima, or, you know, what's your experience in working this out? Does it cause any problems for you?
Yeah, so far I've been running very simple example, and so it works wonderfully, right? But provided that I have very good data, very good amount, so I have no problem of like solving for multiple. I think it's simpler than just discrete choice because you have the continuous choice that also imposing some other restriction, and so in fact, when you are getting the Euler equation, it's how to say it's simpler in a sense because you have more restriction than usually you do with just discrete choice, which is you will have a domain in a sense, and here you get the continuous choice also, so you have both, and it helps. Counterintuitively, it helps to have more to have a more difficult problem in this case.
Yeah, there was one final question. Can the independence assumption between eta and epsilon be relaxed?
Okay, so it could be, but it wouldn't bring anything because if you think about the problem, the point is to have this triangular structure, and that's very important to get this triangular structure. And so in a sense, eta it's capturing everything, and it's also capturing the MD term is capturing the correlation between the general epsilon term and the eta stuff. So if I take it will be faster this way. If I get this here, you can think of a general eta epsilon term, which will include this, okay? Which will include the MD term. And in this case, you have a correlation between eta and epsilon, okay? Which is perfectly fine. But that just by structure, I'm just telling that this is observed and identified, and this is what remains that isn't correlated to eta. So that's why, but it's not a very strong assumption, in fact.
Okay, let's thank Christophe again.
Well, first I want to thank you, everybody, the organizer, and everybody in the room. Unfortunately, I couldn't be there. So this presentation actually followed very much the footstep of the previous one. So most of the most of the setup is similar to what Christophe have done. In fact, I'm interested in the same type of problem, and I will highlight some of the differences with respect to the previous presentation. How much time do I have? Until when? Now is
you have half an hour, including questions. So
including questions, so 25 minutes.
Yeah. Yeah. So
Okay.
Exactly until 37.
Okay. This is joint work with my colleague at LSE, Matthew Levy. As I said, the setup is pretty similar. Agents make complex decisions that involve both discrete choice because of the nature of the good, for example, because are durables, or because some decision require adjustment on transaction costs. So this is so that's required discrete type of decision, but also they do some continuous type of decision. These are taken simultaneously. Some example beside those that Christophe already talked about, which are, consumer choose which retail to visit and how much to buy, which car to buy and how much to drive, which investment to purchase and how much to invest, and so on and so forth. So far, so mostly this type of problem have been studied from distinct literature, meaning there is either they look at just the continuous type of approach, and that is the Euler equation derivation and the estimation of that, or discrete choice model, where just mostly ignore the continuous part and they look at the discrete part. And the discrete choice model, usually the models, the dynamic in the dynamically, I'm looking at dynamic choices. Therefore, while there are some result of identification of the utility function and the discount factor in the Euler equation world, that's not the case in the discrete choice world, but few example. And I have a paper that also talks about that. Whereas there are very few papers, Christophe is one of them, is none of them. Rust have some other paper about discrete continuous choice, and that's exactly what I'm going to study and present today. So I'm looking at dynamic discrete continuous decisions, and I allow the agent to make choices simultaneously, as the framework is very much similar to what Christophe has presented. So the consumer chooses at the same time a discrete choice as well as continuous choice. Therefore, there is a selection issue to solve in what Christophe has discussed about. And so we solve this selection issue in a slightly different way, even though it shares some of the idea that Christophe has already highlighted. In fact, these two papers have kind of been developed simultaneously, and we kind of know about the existence of each other when I present this last year. Then we establish a new set of identification about the utility function as well as the discount factor. So this is one of the difference with respect to, for example, the previous paper, is that we also present result about the identification of the discount factor along the utility function. And moreover, not only we look at binary type of decision, but we look at multivariate type of decision. So the agent faced multiple decisions, decide, what's the optimal thing to do. And another difference with respect to before, we develop a two-step method, which is similar to before, except that the second pass, so this is more a semi-parametric type of estimation. In fact, we estimated the policy function, as Christophe has highlighted before. The policy function can be in principle estimated non-parametric with a polynomial, but we also allow, we estimate the utility function and the discount factor non-parametrically. We use, we leverage our identification assumption, and if I have time, I will briefly talk about that. And we use a pairwise difference strategy, as in Honoré Powell, in order to identify the marginal utility in the second step. And I will highlight some of these features. So the first part is pretty much similar to the estimation is based on this Ots-Miller type of idea, as Christophe said. The second part instead is more non-parametric. It's semi-parametric because we, we need to specify the distribution of the error terms, as I will be more specific in a couple of slides. Okay, so therefore, so the paper has two parts, the theoretical part and then an application that look at PSID data, and we estimate, we apply our technique in order to estimate the discount factor utility function in this type of setup. And we found that discount factor is about 0.91, and there is quite a lot of heterogeneity because we see that for young people, the discount factor approaches to 1, and for people that age 85 or above, it goes down to 0.86. As I said, we also estimate the marginal utility non-parametric, and we found that the risk aversion coefficient is about 0.5 for retired household and 0.3 for working households. Okay, so let me describe the model. So we assume an infinite horizon. So each agent simultaneously chooses a discrete alternative J that belong to a set script J and a continuous quantity Qj. Just, you know, I need to introduce some notation. So we have a discrete, a bunch of state variables. What are those? So let's start from the bottom. So epsilon and zeta it are unobservable shocks. So the epsilon just the discrete choice, whereas zeta is an individual specific shock that affects both the utility, so both the continuous choice as well as the discrete choice. Then we have a bunch of state variables that are observable by the researcher, and these are S and zeta that are discrete and the payoff relevant state variable. Now, make a distinction between S and zeta because zeta will be used as exclusion restriction that allow us to solve for the selection issue. So that's similar to what Christophe called before W. Whereas S are the standard payoff relevant state that are come from a finite space, and LT is a continuous state variable, so you can think that as well, which is, you know, the one that affects the intertemporal budget constraint. So some of I'm highlighting some of the assumption. More detail are in the paper because there are lots of details, but due to time restriction, I just highlight some of the key points. The instantaneous utility function is additively separated in one of the shocks, the epsilon shock. One of the key ingredients to solve for identification is that both the distribution of the unknown the two unknown state variable are known by the researcher. And as I said, both the agent observed both shocks before making decisions, and so that's create the selection issue. And then we highlight some condition independent assumptions similar to what Rust has highlighted in the discrete choice model. And that's are the key elements. Now, the first problem we need to solve is the selection problem, and that's due to the fact that so if you that individual observe both shocks, so when you observe both shocks, you make a discrete choice as well as a continuous choice. If you ignore this fact and you try to estimate directly the continuous policy function, you're looking at the Euler equation, this create selection because the unobservable shock zeta it will affect both the discrete part as well as the continuous part. So therefore, we need to solve for this issue. And the main assumption that we use, so this is quite different from what Christophe has highlighted, is we use this unlimited encouragement type of idea. Remember, we have script J possible discrete choices. And so what we need is that exists at least one discrete choice such that for all other choice, The marginal utility is independent from this zeta, which is the exclusion restriction we need, but we need them for all j but 1. And also we need that there is a sequence zeta such that the probability of choosing a particular choice j, different from k, approach to 1 as in the limit. So suppose a consumer need to go to a supermarket and buy some stuff. In particular, suppose that the consumer lives in Manhattan, need to choose between going to the local bottega or go to Costco in New Jersey. What we need is that so our instrument that allow to identify exclusion restriction that allow to identify the selection issue in this setup will be traffic, because if traffic is sufficiently bad, then we need that to affect the discrete choice of going to the local store in Manhattan. And we need that when traffic is sufficiently bad, the probability to choose that local store approach 1. But we don't need that this traffic condition affects the probability of choosing to go to Costco, if that's, and moreover, we can allow also the marginal utility of the majority of the agent to depend on the traffic when it goes to New Jersey. Maybe, so that's possible in our setup. So that's the kind of idea we have in mind in order to solve the selection issue. So based on that assumption, we show in the paper that we can identify the unobservable shock zeta, as well as the continuous policy functions. Then we proceed to identify the full model, so the marginal utility, discount factor, and then the level of utilities. Now, I will highlight what are the key elements we need, and hopefully talk a bit more about the strategy of identification and the application. It can be written in recursive form. So the agent choose, what's as two choices, the discrete choice as well as the continuous choice to maximize the present discount value of utility that can be written in terms of the value function, subject to intertemporal budget constraint. The budget constraint is pretty standard. FJ, you can think that to be the interest rate, and we allow that to depend on the state variable. More detail, as I said in the paper. So as a definition, we can also define the conditional value function to be the small j, which is the optimal choice. So is the present discount value of utility chosen the optimum for alternative j when consumer choose optimally q. So that's q star. And notice that because of the max operator in the value function, that's typically not concave, but in fact, in the paper we talk more about that feature of our model. So if we combine this result together and we look at the continuous alternative, we can write down a generalized Euler equation that you see is pretty much similar to the standard Euler equation, except for the second term on the right-hand side, inside the expectation. You see that term there, the derivative of phi j, the derivative of phi j with respect to LT plus 1. That's exactly the derivative of the surplus function that comes from the discrete choice. So now if you assume that the error term is extreme value, for example, that phi j, that's the derivative of the log probability of choosing j with respect to L T plus 1. So that's the main difference. And therefore, so that's what, without that term, we have the standard Euler equation that people have looked when you ignore the discrete choice. And notice that that term, you can think that is, because it's linked to the discrete choice, therefore, the discrete choice probability, therefore you can think that that term is observed in the data once you estimate the policy function in the first step. Now, what this Euler equation, generalized Euler equation, tell us? So if you don't have a discrete choice, the Euler equation equates the marginal utility today or the marginal utility tomorrow for the same alternative. Now, because you might choose different alternative in the future, that equivalence is no longer true. Therefore, if you use J both on the left and right hand side, you need to account that J in the future might not be optimal. That's the role played by this derivative, this second term there. Okay, so just to give you a flavor of what's the difference, and I'll talk more how ignoring that term, in fact, makes the estimation of the Euler, if a discrete choice is present but ignored, the presence of that term, because it depends on the state variable, makes the instrument usually used in the standard framework not valid. Now, based on the assumption and the idea that I've discussed so far, we prove in theorem 1 that both the discount factor as well as the marginal utility are point identified. Now, in order to identify the level of utility, we need to make a normalization. That's kind of standard in the discrete choice world, because you need to normalize. When you look at the probability, you make just you make a pairwise comparison among alternatives, so you need to normalize one alternative in order to identify the level of utility. In particular, in this framework, what we need is that we need to take one alternative, let's say alternative 0, and we need to normalize utility of 0 when you choose 0 to be 0 for all state variables. Once you have that normalization, then you can identify non-parametrically both the utility function and the discount factor. Now, as I put in theorem 1, the discount factor can be function of state variable as well, and that's what we do in the application. So in fact, our theorem allows the discount factor to be function of state variable. And in our application, we allow the discount factor to depend on age of the individual. So this gives you a brief overview about the theoretical results. Of course, there are lots of details that are in the paper. Now, I want to talk briefly about the application, also to show how we can non-parametrically identify the marginal utility in the second step. So, in particular, we are looking at the consumption savings retirement type of problem, where an individual choose. So we use the PSID data US, and here individual choose how much to consume, but in every period they also choose if to retire or not. So we use the PSID from 1999 to 2017. We follow Blandel et al. To construct a measure of consumption. Also, because so individual in different tax bracket, we compute what exactly is the net interest that they receive based on the tax bracket they fall in, using the NBR taxing software. And we use the return obtained for the interest rate from the Federal Reserve Bank of St. Louis. This is a brief statistic about the data. The main difference with respect to other studies about the PSD panel is that we look at both people that are working and people that are retired, because we endogenize that choice in our framework. And so you can see that there is some heterogeneity in the level of income, the level of wealth, the level of consumption between working and retired individuals. So let me highlight briefly the estimation procedure. So it's a two-step method. The first step we retrieve the policy functions, and also we use our result in order to recover the unobservable shock. So we solve the selection problem in the first step. In the second step, we estimate the marginal utility as well as the discount factor. And as we said, we leverage our proof of identification, and we apply this pairwise differencing strategy, first highlighted by Honoré and Paolo in 2005. So let's look at the first stage. In the first stage, we need to estimate the discrete policy function. So we estimate, we do this by simulating maximum likelihood. We get the discrete choice policy. For the continuous choice policy, now in this particular setup, what's zeta? Remember, zeta is our exclusion restriction. Now zeta is your previous decision. So zeta will be what's your previous discrete decision. So in particular, if you have decided to retire, now no longer in the next period you no longer have this discrete choice to make, and therefore you can infer the unobservable shock directly by looking at the quantity consumed. And in fact, we estimate a policy function here. You can, using some sort of polynomial, and based on this polynomial, you can retrieve, based on the assumption that we know that the distribution of zeta it, in particular the unobservable shock, in particular we assume that's normal. So therefore we can retrieve the policy function zeta it, and also we can retrieve the conditional zeta it, so conditional on the state variables. Therefore, we take this result and then we look at people instead that working, and then from people that working, we can retrieve the conditional value, the conditional policy function, the conditional value of zeta it, and then using the law of total probability, we can combine that with what we have retrieved for the retired people in order to get the zeta it. There are a few details there, but this sort of gives you the idea how this works in practice in this particular application. The second, so the second step, as I mentioned, we leverage the idea of the proof in order to estimate non-parametrically the marginal utility and the discount factor. In particular, now think about, so pretty much this follows the step of the proof of theorem 1. Think about, so remember we have solved the selection issue. We have zeta it. So we now just focusing on the estimated marginal utility, and therefore we just focus on the generalized Euler equation as I showed before. Think about having two households that make, I and IT that might have make different discrete choice. So one choose to work and the other to retire. Now, using the discrete choice equation that I highlight down there, you can always write the conditional value function of working to be in terms of the conditional value function retired, and vice versa. In principle, because this individual makes, so in principle, this individual have different state variable, in particular might have different zeta it prime are potentially different. Now, what do we do? So we take the two generalized Euler equations I showed before, and then we try, the idea of the proof is that we need to, if we look at the generalized Euler equation, there are lots of unknown, because we have the marginal utility on the left-hand side, the marginal utility on the right-hand side, that depends on potentially, different states. So what we do is trying to reduce the number of unknown. How do we do that? We do that by taking the difference of the first order conditions in order to remove the unknown on the left-hand side. So the marginal utility at time t. So if we have infinite data, that's easy to do. You choose, individuals that have exactly the same state variable today. They choose the same quantity, and that's, but have different zeta and zeta I prime, and that's done. In practice, we don't have infinite data, we have a sample, and therefore we need to replicate in the sample the same kind of idea. And we do that by using this pairwise difference approach. So first, as I mentioned, we take the difference of the first of the condition. So if you take the difference in the first of the condition, you have something like equation 3. Now I need to mention that what I show here in the slide is based on the idea that the marginal utility is additively separable in zeta it. We generalize that in the paper, but I think it's simple to see this version on for the presentation. So if we take the difference between the first of the condition and we assume that we take two individuals that have the same state variable and choose the same quantity today, even though they choose a different discrete choice, you get something like equation 3, and you see that what is in equation 3, the left-hand side is known in quote because d phi dl is just the derivative of the log probability, as is the derivative. I'm expressing the conditional value function of one individual in terms of the other, so therefore phi in general will be the log ratio probability. I write that phi. So, and because it's the first of the condition, I take, that's there. I'm using also the envelope condition to derive equation 3. But the left-hand side is known, and I take the difference because I want to get rid of the marginal utility for both individuals. On the right-hand side, I have the discount factor, the interest rate, which is RW, and R, which potentially are different again, because these are the net of tax interest rate, and therefore they are potentially different because we are looking at different individuals that have different potential wealth or income that are not payoff relevant. And the script V is just what I showed you before in the previous generalized Euler equation, is the marginal utility time t plus 1 plus this adjustment term, again, that depends on probability, and therefore you can think that this term is also known. So this phi r is known. So the only unknown are these are the marginal utilities. So of course, as I meant, so
That's fine. Sorry to interrupt. I think you have like 2 minutes remaining, so you might want to slowly come to the conclusion so that we can also discuss a few questions. Thanks.
Yes. Okay. So from here we get the equation to estimate. So we remove the expectation. We add the error term. We have basically some sort of regression, like equation 4. Where upsilon, the left-hand side part, and is known. X is also this adjustment term that are known, and the only unknown are the marginal utility. We model the marginal utility as a spline, a linear spline, and again, because we can't match individuals that have exactly the same state variable because of the sample, reduced data in the sample. We use this idea of Honoré and Powell, and we assign to each pair of individual a kernel weight that depends on the distance in the state variables. So once we have that, basically our estimator, this equation 4, if we assume, for example, delta is just an unknown, independent of any state variable, that's really a simple weighted least square. But because we allow delta to depend on the age, then it becomes a weighted non-linear least square because of that, because we have this interaction kind of term. And so we proceed and estimate the discount factor, the marginal utility. This is our estimate of the discount factor. You see is decreasing in age, as I mentioned at the very beginning. These are non-parametric estimate based on the spline of the marginal utility. Now here you can see that these are different marginal utility that depends if you're working or retired, and depends on if your composition of households is greater than 2 or lower than 2, and your age is above or below median. So the state relevant payoff, we follow the literature. Therefore, we just assume that the marginal utility depends on household size and quantity and age, because we allow the discount factor to depend on age. So given that this is based on spline, actually we're quite pleased with the result. You see that the marginal utility of working is always above the marginal utility of retired. They all look kind of downward sloping. We also compute, based on the estimation of the coefficient or relative risk aversion, and which can be done again non-parametrically, and therefore we found that it's about 0.5 for retired household and 0.3 for working household. Conclusion. So we set up. So our paper set up all of the points in order to identify the discount factor and the marginal utility non-parametrically. We also give a way to estimate the whole model in a semi-parametric way, where again, a semi-parametric we need to, because we based on the assumption the unknown, everything else is actually non-parametric. And our result seems consistent with what other people have found, with our prior intuition. Especially we found a lot of heterogeneity in discount factor. That's all, and sorry for being a bit over time.
Thank you very much for this presentation. So let's give Pasquale a round of applause. So in the interest of time, I think we have time for 2 questions. John Rust was writing one in the chat, so I will pass over the microphone to him. And is Juan also here?
Thank you. Yes, I just, both very interesting papers, but we know that consumption is really hard to measure. There's a lot of measurement error. So what does measurement error do to your estimation identification? How do you deal with that?
In fact, we are at the moment we are ignoring that aspect. We are not considering the measurement error so far. Something that we are thinking about, but at the moment is not there.
So there are like also similar as in the previous question paper, Juan is asking if one can relax in your paper the independence between zeta and epsilon. So he's thinking of unobserved shocks like health shocks that might affect both marginal utility and the utility of work.
I mean, yeah, that's actually, it's a challenging question. I'm not sure that, I mean, as Christophe has already highlighted, in fact, I don't think that we are missing a lot by making that assumption. I mean, I agree with what Christophe has highlighted before. Technically, though, I don't know if we can actually relax that.
Okay. Okay, thank you very much, Pasquale. I think there were like one more question in the Zulip chat. So if you are joining as well to answer that one, that would be amazing, because now I want to let people go for lunch because otherwise our lunch break gets too short, such that they will break.
Okay, yes, I can stay around. Yes,
that would be fantastic. So thanks a lot, everybody, for participating, and thank you, Pasquale, and thanks.
Thank you.